So consider an example of a regression problem. In this, we have seen that we are trying to form an equation y equal to mx plus c. Okay, by using, we have seen how to find out an equation or how to form a line equation using the existing data, historical data of x and y. Given the data of x and y, you are trying to form a model like this. However, when you are forming a model, you are trying to find out the value of m and c. Okay, so example can be simply like this: 10x plus 3.5. You get an equation like this by considering the data which is given to us of x and y. Now, once you form this equation, we try to test this model. When you try to do testing, we find out that the value which is generated, the value which is predicted, okay, by our method, and the actual value, both are differing with some error. Maybe for example, if for given x equal to 3, this is 33.5 and the actual value is 34, assume. But the equation which I formed is this using the regression. Now you can see there is a difference of 0.5. So there is a difference of 0.5 in the values which we have predicted and the actual value. So we are trying to improve this regression equation. Okay, so we are trying to improve this regression equation such that the value which we are predicting is closer to the actual value. The value which we are trying to know predict should be closer to the actual value. For that, we have to optimize this function. You have to optimize. You have to optimize this equation mx plus c. We have to optimize. Why do we have to optimize it? So that we get the better values of this weight and the bias, such that the error rate between the actual value minus the predicted value is negligible, or it may not be zero, but it is near to zero. Then we say the regression model which we have formed for prediction is best model. Okay, so there are different, I also said that there are different techniques for generating this regression equation. To generate a regression equation using the data, we have different techniques. We have seen one technique of doing it. So we got, you saw the formulas of forming this line equation. Now we have to optimize it. How do we have to optimize this? So we use a technique called gradient descent. Okay, gradient descent. Let's try to understand. If you take a simple function y equal to f of x equal to x square, I have a function f of x equal to x square. If I plot the lines, if I plot the graph of that particular y equal to x square, it looks something like this. This is my y-axis and x-axis. So if you plot a graph for y equal to x square, you get an equation like this, right? So even if you give minus values, you get positive y values. Now, the equation of I'm taking a simple example, but again here, mx plus c. Now, I want to have an accurate model for this. So what we try to do, we try to choose a point here. We try to choose a point somewhere here on the line and check whether at this point, this particular equation is optimal or not, or is it giving the best values or not. Okay, then if I observe that when I'll try to reduce these values slowly. I will check for every value. Okay, for this y equal to x square, the optimal values are at this point 0 comma 0. We have the best values. So at this point we're having the best values. So what we're trying to do, we're randomly on this line equation, randomly we are choosing a point. This is the technique of gradient descent. Randomly choose a point on this line. If you choose a point here, this side, if you choose a point here, then you try to, when you choose a point here, you try to increase the value and see whether it is giving better values or not. If not, you try to change the direction to downwards. You try to reduce the value of x. Our goal is to find out optimized values. So what we are trying to do in gradient descent, randomly select one point in the line. Okay, try to find out the error value. Try to find out the error value and check if that error value is low or high. Then once you choose this point, suppose you choose, let me check another color. Suppose you choose this point first. After choosing this point, then you go for this point, second point, and you observe the error. Is the error increasing or decreasing? When the error is decreasing, it means you can go still in the same direction. You can reduce the value of x, then reduce the value of x, then take this point, then take this point. You keep doing this like this. At a certain point, the error will be very, very low. After maybe this point, once you reach here, the error is very, very low. After this, when you take another point, you increase the value, you go for another points like this on this variable, you see that the error is again increasing. You see that the error is nothing but the difference between the actual value and the predicted value. Difference between actual and predicted value, right? So after procedure is randomly choose a point on the line, then try to slowly increase that value. And if you're observing that the values are the error between the actual and predict, or the error variable is reducing, at certain point of time the error variable will be very, very low. From there onwards, the error will again increase. So at that point where the error value is very, very low, that values are the optimal values of m and c. These are the optimal values of m and c. So the earlier equation of yours, that was 10x plus 3.5, will now may become, it is something like 9.8 plus 3.43. It may change like this. So this becomes your optimized equation, which gives better results or better accuracy. It means the error is very, very less. Now what is our function? Which one do we have to optimize? Right? So I am saying equation is y equal to mx plus c, and my predicted value is y cap, for example. Okay, this difference I want to reduce. I want to find out the difference between y minus the actual value y, that is mx plus c. This is the difference between the calculated and the actual value. This difference we have to reduce. The difference between the actual and the predicted we have to reduce. So what we have to do, we have to optimize, we have to find, reduce this error. We have to minimize this function y cap minus mx plus c. So when you minimize this, at certain point of time, you will observe that for given values, for certain values of m and c, for certain value of m and c, this error is very, very low. There we stop our procedure and we finalize our m value and c value. Okay, we will understand this better with a numerical example. Here we have to use partial derivative of this function f. Okay, so your objective function is to minimize y cap minus mx plus c whole square. This you have to minimize. Why you have to minimize this? How I got this? This is the predicted value, this is the actual value. The error difference should be very, very low. That's what my function is, minimize. So this is a function f, which is minimize y cap minus mx plus c whole square. I have to minimize this. For minimization, we find out the differentiation and we try to find. Let's see with an example the procedure. Numerical example, you understand better how to do this. So we are given, so your cost function, which you have to reduce, is given as uh, summation of I equal to 1 to n y bar minus mx plus c whole square. This you have to minimize. So in optimization technique, we use what I said here. You randomly choose a value. Okay, randomly choose one value in the line. After randomly choosing a line, you try to find out the whether it, for that particular randomly chosen value, this cost function is minimal or not. If it is minimal, then you find out the new value. So this is randomly chosen value is old. You have to calculate the new value, new point, right? If you remember when I was explaining this, In this graph, you randomly choose a point here. At this point, you find out the error value. Then you go for next, choose this point. Check whether the error is decreasing or not. If it is decreasing, proceed in the same direction. Keep changing the values. Keep decreasing the values. Okay. After certain point of time, you will find. So what is this? This is my old value, which I have randomly selected. This is my new value. So which one to select my new value? Should I take like here? If you see, so this is 0. I'm writing x-axis values 2, 3, 4. Here minus 1, minus 2, minus 3. So your equation is something like this. It means you have point for 1, you have point for 2 here, point for 3. Here you have 4, minus 1, minus 2, minus 3. Assume you have taken minus 3 in the first case. Randomly you have chosen minus 3. Okay, then should you directly, this you found out a value. Now you want to test it with another value. So you are choosing minus 2. Should you directly take minus 2 or should I take any values in between here? Maybe sometimes if you take minus 2, your value is again increasing. Okay, your value is increasing. So what is here the difference here? I'm reducing 1. Again I'm reducing 1. Again I'm reducing 1. This way I'm testing. So this parameter which I'm keeping as a variable is 1. Okay, should that is your step value actually, step size. After choosing a random value, after choosing a random value, okay, after that you are following a particular step size. You are not increasing one. If you are increasing one, step size is one. Why? Because you are reducing minus 3, then minus 2, then minus 1. So you're with one difference, you are reducing the value and you are checking whether the error is decreasing or not. In that case, your step size is 1. So what should be our step size? Should it be 1 or not? That also we have to find out. Because sometimes if you give minus 3, your error is around some 0.15%. If you give minus 2, your error may become again, it may increase to 0.45. In this case, we do not know that we cannot take minus 2 as our next new value. So your step size should be very, very small here. Maybe you have to increase zero point 0.1, zero point 0.1, zero point 0.1 and check whether you are getting the best less error or not. Okay, so this is about choosing the step size. So there are a few terms here. Let me explain once again. In optimization, we have a cost function. We have a cost function that is nothing but y cost function is given as like this, summation of I equal 1 to n yi minus y cap minus mx plus c or yi minus mxi plus c whole square. Okay, you should have a randomly selected value, randomly selected value for m. We will randomly select a value for m. Then why m I am selecting randomly? Because m is the one which I want to optimize. Then define the step size. Define the step size. Then find out the new value. Find out new value for m. So when your equation is y equal to mx plus c, after first iteration it should become m1 x plus c 1. Then y equal to m2 x plus c2. Like this, you are changing the values of m and checking whether your model is giving less accuracy or not. Right? Let's take a simple example. Let's try to understand this procedure and try to solve this. So we are given a very small data x and y as 1 2 and 3 4. X values are 1 2, y values are 3 4. So initial values of my equation is y equal to mx plus c. So first step is to initially assume few values for m and c. I will assume this is my equation or data given to me. I'll assume c equal to 0 and m equal to 1. So what does my equation becomes? Y equal to x. This is my equation. Now I have to find out the partial derivative of this. I have to find out the partial derivative for this. How do you find out partial derivative? We have to calculate the new value and the old value as well, right? So this is your old values. These are your old values. So there is something called as learning rate. There is a parameter we use very frequently in machine learning is learning rate. Generally, this learning rate is very, very less, 0.001. It may vary with the algorithm, but the standard learning rate is 0.001, 0.001. So when you do optimization, when you find out a new value, how do you find out new value? New value is nothing but old value minus step size. Old value minus step size. That's what, no? If old value is minus 3 and step size is 1, it becomes minus 2. Right? 3 minus 1, 2. It is reducing. I have taken 3, then I am reducing my value, it becomes 2, then I am reducing my value, it becomes 1. How? When the step size is 1. So this way, new value is nothing but old value minus step size. Now, what is your step size? How to find out this step size? Step size is nothing but your learning rate into your partial derivative value. Okay, learning rate into your partial derivative value. We will see this with a numerical example. Let's see how we try to find out the new step size value. So given x and y values, very, very small example. These are the values. Assume c is 0, m is 1. I have to, first step is to find out the partial derivative. So what is our cost function? Cost function j is given as summation of I equal to 1 to n yi minus mx plus c, this one whole square, right? So let's see what is the value. So what is y1? So this is x1, x2, y1, y2. So what is y1 value? Y1 value is 2 minus mx plus c. M value, which we have assumed 1, and x value is 1, 1 plus c. C is 0, so nothing is there here. This whole square plus again y1 value, y2 value is 4, 4 minus mx, m value is 1, x value is 3. So 3 plus c value is 0, so it doesn't make a difference, right? If you do this way, if you just find out this difference, but along with partial derivative, no, sorry, we forgot one step here. We have to find out the partial derivative of this. Find out the partial derivative of this. What is the function? It is made up of m and c. So find out the partial derivative with respect to c. So dou j by dou c. So what does this becomes? This becomes 2 is the partial derivative for this. How do you find out? It is nothing but 2 minus m plus c. 2 minus m plus c. M 1 into m plus c. I'm not considering c. I'm considering only m value. This is whole square plus 4 minus, because 4 y2, no, 4 minus m value is 1, so 1 into m plus c, 1 into m, 3m, because here it is 3 whole square. So if you do the derivative of this, you may find something. For this it is 2 into minus 2 minus c plus m. See, this 2 comes here plus, and again you get here minus 2 into, you have the value as 4 minus 3. If you substitute the values of m and c, you get the value as minus 4. Okay, maybe once you understand how to do this derivative, we'll see. I'll repeat this once again. I know it's not clear. Let's take another example which gives more clarity. Yeah. Age and salary. Let's take a bigger example. I'll directly give the regression equation. From there we'll try to solve this. So age values are given 30, 37, 25, 43, 50, 29, 46, and the salary values 800, 950, 600, 1050, 1200, 740, and 1100. So this is our data given to us. Okay, I am trying to find out a relation between age and salary. Fine. What I have to do first step, assume our equation is y equal to mx plus c. Assume some value for m. Assume some value for m. Let us assume m is 300 and c is m is 10. Let's assume m is 10 and c is 300. M is 10, C is 300. We need to define a learning rate. We have to define a learning rate. Let that learning rate is nothing but 0.0001. Let this be our learning rate. Now using this, what is our equation, current equation? Y current is nothing but 10x plus 300. This is our regression equation which we formed using some assumption. Now what we have to do, once you form this, you have to define your cost function. What is your cost function? Cost function is nothing but 1 by n summation of I equal to 1 to n yi minus mxi plus c whole square. This is my cost function. Now you try to find out this value. You try to find out the value. What is the cost, current cost value? Current cost value. So you know yi. What is yi? 800 for y1, 30 for this equation you already know, 10x plus 300. So I'll just simply write one line here. It is nothing but 1 by n of what is 800 minus mx plus c. What is x value? 30. 30 into 300. So 30 into 10 plus 300 whole, okay, whole square plus so on you have to go. So this is 600. So that is 200 whole square. Like this, if you found out the cost, initial cost value, if you substitute all these values, you get the cost as something like this. That is 74485.714. I think till now it is clear. What I have done here, given the data, this is my line equation. For this line equation, I have assumed few values of m and c. After making some assumption, this becomes my line equation. Y is equal to 10x plus 300. I have defined the learning rate also. I have find out the initial cost. With this line equation, I am getting the cost value as this much. Now, the next step is to, you have to find out the partial derivative. To reduce, to minimize the value, what I have to minimize here? I have to minimize this cost. I have to minimize this. I have to minimize this cost. To minimize, what I have to do? I have to find out partial derivative of this. Let's try to find out the partial derivative for this equation. So for the partial derivative for cost function, partial derivative cost function with respect to m, if I do, so what is, let me write the equation once again. So we have our cost function as 1 by n summation of I equal 1 to n yi minus mxi plus c. This I want to find out the derivative of cost function with respect to m. So how it will be? 2, this becomes minus 2 by n, minus 2 by n summation of I equal to 1 to n. Here I have yi minus mxi plus c into, with respect to m, this becomes x. Because this is the only value. This is constant, this is constant. With respect to m, this becomes into xi. Now this is your value. Now here you substitute the values of yi and xi. Here you substitute the values of yi and xi. So when you calculate this value, you get something here minus 20.20388.57. Minus 2038.57. Our goal is to reduce this cost. How I got this cost? If I assume m as 10 and c as 300, this is my cost. I want to optimize this cost. For that, I have done partial derivative. After doing partial derivative, I am finding the value of partial derivative. I am finding the value of partial derivative. That is minus 2 by n summation of I equal 1 to n yi minus mx plus c into xi. So you know the values of y, you know the values of m, you know the values of xi and c and xi. If you calculate, you get this much value. Now find out the new value for m. New value of m is nothing but old value minus step size. Step size is given by Step says how you get it. Learning rate minus learning rate into your partial derivative. So old value was of m was 10 minus learning rate is 0.001 into we get this dm as minus 20388.57. If you multiply this and find out the new value of m is nothing but 12.03. 12.03. See here, what I assumed m as 10. Now what did I get? 12.03. How I got the new value for m? How I got the new value for m? Using by finding out the partial derivative of this function, cost function, with respect to m. I got this value. Substitute these values, find out a numerical value. Third step you see. Same thing you do. Now find out the derivative of cost function with respect to c. With respect to c. So this function, this with respect to c, you have to find out the partial derivative. So when you find out with respect to c, you get the equation something like minus 2 by b into summation of I equal to 1 to n. I get yi minus mx plus c. yi minus mx plus c into 1. This in brackets. Into 1 because with respect to c, everything else is a constant. So c becomes 1. Now here you substitute all the values. You are finding dc value. You substitute your yi, xi values, m values, c values. That is m is 10 only. You substitute everything. You get dc value something as 300.0497. So this is this value you got for d. Oh, sorry. D. No, not I directly jump to one more step. So you get the value as something. Sorry. Sorry. Right. So you get if you calculate this value, you get this value as minus 497.14. Now you have to calculate new value for B. How to calculate new value? Old value of B minus learning rate into DC. So old value of this is 300 minus learning rate is 0.001 into this is minus 497.14. When you do this, you get the new value as 300.0497. This is your new value for B. So if you observe here, you have new value for M as 12.03. You have new value of B as 300.0497. Now, what is your new equation? Instead of previously, we had 10x plus 300. You had 10x plus 300. Now, instead of this, you are having new value as 12.03x plus 300.0497. This is your new value for y. Using this, find out the cost value again. Find out the cost value again. How to find out cost value? What you've done here, apply in this formula. Apply in this formula, get the cost value. Get the cost value for this new function. See, m has changed, c has changed. For this new function, find out the cost value. When you find out cost value, I think I already have this 39084.8289. Okay, 39,084. What was previous one? 74,485 with 10 and 300. But when I change that value to 12.03 and 300.03, the cost has reduced a lot with this new value. Repeat the same procedure again. Okay, what procedure I have to repeat here? Again, go back, find out the derivative value for the new function, find out dm value, find out new value of m. Repeat this procedure until this error value is very, very low. Okay, until this error value is very, very low. That way, after doing certain experiments, you will get a new values for m and c. So with this 10x plus 300, your equation will something change, something like, let me write it just a second. It will change something. The y final will be something around 13.65x plus 301.12, right? Yeah, this is C actually. This is C. C. Sorry, by mistake I wrote here. This is C. C. New value for C, not B. It is C. Mx plus C. Okay. I'll quickly now I will summarize this optimization. What we have seen, the steps in this optimization of, you have values of x and y. Okay, you have values of x and y given to you. For this, your equation is y is mx plus c. Mx plus c. Assume values for m and c. With that, you form an equation. Okay, so let me assume the value of m as 10, x plus c as 300. You assume this. When this is the equation which is formed using assumption, find out its cost. Cost means difference between the actual value minus predicted values. How we do that? 1 by n, summation of I equal to 1 to n, yi minus mxi plus c whole square. This you find out. Keep this aside. You find out this value, keep this aside. Now, let this be your cost function. Find out, let this be your cost, COST, or let me use the word J. J is the cost function. Once you find out the cost value, keep it aside. You assume some values, you keep this aside. Now, you try to do partial derivative of J with respect to M. You do this and find out its value, numerical value, by substituting the X and Y values. Okay. When you substitute that, you get a derivative value dm. With this, you find out new value for m. New value for m will be old value m minus learning rate into your dm. You get new value. Similarly, find out the partial derivative of this cost function with respect to c. You find out its value. Then you calculate d. You have dc with you. Now, new value for C will be old value of C minus learning rate into DC. So you get new value for C. With after doing these steps, you have new values for M and C. You have new values for M and C. Then you try to calculate the error again with that new equation and see whether the error is reducing or not. You have to keep repeating this procedure until you get an optimal values for M and C. It means, how can you decide that we get an optimal values? See, M initially was 10, later it became 12.03. So C also will take 300. Here it became 300.0497. And the cost value, it was something 74,000, later became 39,000. You increase this to 13.06 and you get 301 point something. This becomes maybe directly 7.5k. Again you increase to 13.72 and 301.56 something. You get here just maybe around 0.05. It reduces. After this, if you increase, make it 14. This will again increase. It means you have to stop here. So these are your optimized values for M and C. With this, you get an equation. The new equation has 13.72x plus 301.56. Okay, this procedure you have to keep repeating it. This way we try to optimize it. But in Python programming, it's just one algorithm. You form the equation, you apply gradient descent technique, it will give you the final value. So by default, somebody who forms a regression equation, it is along with optimization. You have to by default write the optimization also, so that you get an optimized values for M and C and your equation is best. Why are we trying to optimize it? Because we want our error to be less. Error to be very, very less. What is error? The difference between the actual value and the predicted value. Okay, predicted value, why? Because I'm talking about regression. Regression is used for prediction. During prediction, I form a line equation. That line equation might not give me better results. I have to optimize it using gradient descent technique. What is gradient descent technique? Randomly choose some values for M and C, find out its cost value, keep increasing slowly that value of M and C, and make sure that the errors are reducing. The error cost value is reducing. When this cost value is reducing, then at certain point the cost will reduce and then increase. So at that particular point, we have to stop our procedure. And how to know whether it is increasing or reducing? You try to plot a graph for those cost values. So it will be some point it will be increasing, and then it will decreasing. So when it is decreasing, we know that that is the optimized value. Oh, sorry, it's reverse. It will be decreasing, and then it is increasing. Okay, so when it is decreasing, it's fine. At certain point, it increases. Stop at that particular point. Finalize your M and C values. Finalize your M and C values and stop the procedure there. Okay, this is about optimization using gradient descent technique. Here, vector calculus is used in finding the derivatives of the cost function. That way, these are used in dimensionality reduction as well. When you go for neural networks, there also we have weight and bias variables. So we try to do optimization there using partial derivative, and we form a better neural networks. The function for neural networks, we form a better one, right? So this is about optimization using gradient descent.